At Seco Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, Seco helps ensure you achieve real results. No matter your need, Seco has you covered. Simplify your environmental initiatives with our Seco Environmental family of industrial solutions brands. Seco Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, Seco helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit secoenviro.com today.
Welcome, and thank you for joining us today for the Seco Certified Continuing Education Series. Today, we will be learning about industrial ventilation basics presented by Seco Environmental. My name is Mary Rusnak, and I'm the Marketing Manager for the Industrial Air and Fluid Solutions segment of Seco. And with me today is Vern Bueller, Applications Engineer, and Dale Tompkins, Project Engineer for Seco. While we wait for everyone to join, I'd like to go over some basic housekeeping items about the webinar platform and also the PDH certification. So first things first, sound issues. I know obviously you can't hear me, but hopefully you can see the screen here. So check your media player, which is the orange arrow. Is the mute button on? Otherwise, check your blue arrow. That is the help widget, and that will help you with some troubleshooting. Finally, log out, log back in. Hopefully that will get you where you need to be. At the bottom of your screen are multiple application engagement tools, or what I call widgets. All the widgets are resizable and movable, so feel free to move them around and just make them a size that works best for you. If you have any questions during the webcast, you can submit them through the Q&A widget. To keep ourselves on track, all the questions are going to be held until the end of the presentation, but you can submit them at any time. If we don't get to your question, don't worry. We will definitely reach out to you after the event and make sure that it is answered. A copy of today's slide deck and additional help materials are also available over on the resource list, which is on the right-hand side. And we encourage you to download any resources or links that you may find useful. Also, if you take a look over there is the industrial ventilation summary, which is hint, hint, something that would be helpful if you are taking the quiz later on. The PDH or state information is also listed. What you're going to find is that we give credits for 36 states. Finally, if you just hover over the widgets, they basically will tell you what they are. One of the widgets you might want to check out is the checkmark widget, which will take you to the secocertified.com, which you will find our on-demand events. After today's event, we will have 5 on-demand events available for you to go and check out at any point in time. So feel free to go back there and take those events if you haven't taken them already. Also, if you check back later next month, you will see that our first quarter events for next year will be listed. So check back for our schedule in the future. We are planning on doing 8 events next year, so definitely come back and check out the schedule. Finally, the last 2 widgets are the ones that are most important for anybody who's taking the PDH portion of the quiz or of the presentation. The first one is the test widget, and that's where you're going to find your test. The second widget is your tracker widget. And that's where you'll basically see if you have completed everything that you need to get your PDH certification. Once you have completed everything, there will be a print box that will pop up on that tracker widget, and you will be able to print out your certificate. So finally, webinars are really bandwidth intense, so make sure you close out of anything that you don't need to have open. If you find that your slides are lagging, push F5 on your keyboard, and that will refresh the page. I've also found that Chrome seems to work best in terms of browsers. Again, if you have any additional problems, just go to the help widget, and hopefully that will answer all of your questions. An on-demand version of the webcast will be available after the event and can be accessed using the same audience link that was sent to you earlier. All interactivity remains, including testing capabilities. So in terms of the PDH portion, today's webinar is worth 1 professional development hour. You must be present for at least 50 minutes, and you need to pass 8 out of 10. So make sure that you fulfill both those requirements, and then you'll be able to go to that tracker widget and print out your certificate. We suggest that you keep a log. We will keep a log of this for 6 years. And if you have any questions, just email me. You know, you can also use the email button, or widget, I should say, at the bottom of the platform, and that will email me directly as well. The webinar is 1 hour long, but we will keep the presentation open for about an additional 30 minutes after the event, so that you guys can finish up the quiz or print out any materials that you would like. We do have a lot to go over, so I'm going to try and speed through some of this here so we can get to the actual presentation. So in terms of the outline for today, we're obviously going to talk a little bit about industrial ventilation versus HVAC. What's the difference? We're going to talk about some equations. We're going to look at hoods, ducts, and fittings, best practices, and then we're going to go over a couple slides of shame, which basically is just showing some unusual configurations for industrial ventilation. But before we get to the presentation, let's start with a poll question here. And if you've attended our events before, you know that you will actually be able to answer this question on the next slide. So how much experience do you have with industrial ventilation? I'm an expert. I have some experience. I have a little experience. I have no idea what industrial ventilation is. And here's where you can answer the question. All right, another second, and let's take a look at these results. Okay, we have a really nice split here. It looks like we've got, you know, pretty much about a third across the way that are in various areas, having some experience, little experience, or maybe nothing at all. So I think that everybody in this presentation is going to get something out of it. So I'm going to now turn this over to Vern, who is going to start the rest of the actual presentation. Vern? Vern, are you muted? Vern, are you muted? Hold on for just a second. It looks like we are having some technical issues. Stand by, please.
Hello?
Vern, is that you? I apologize, everybody. I'm not sure what's happening with the sound
Hello, Mary?
here. Yes,
Can you hear me?
I can. All right. Can you hear me?
Yes.
Okay. Apologize, everybody. Thanks for
I apologize. Can you hear me now?
Yes, we can hear you.
Okay. Thank you, Mary. We wanted to begin and distinguish between industrial ventilation and HVAC. The first bullet point is a good and simple definition by stating the objective that industrial ventilation prevents employee exposure and associated adverse health effects associated with airborne occupational hazards. Industrial ventilation is also a means of meeting emission requirements for surrounding neighbors and permitting authorities. Captured emissions are routed to a control device such as a scrubber, a thermal oxidizer, or dust collector to reduce pollutants if required. And then the emissions are discharged to the atmosphere. Industrial ventilation is not HVAC. HVAC is the indoor heating, ventilation, and air conditioning for environmental comfort. It may seem obvious, but yet be sure your design improves the conditions of the employee as well as the environment. Good designs, the figures on the left of the screen, control and contain hazardous concentrations of toxic materials. And they also remove undesirable odors and dust. 3 questions as far as the exposure for hazardous assessment will tell you if there is a need for industrial ventilation. The 3 questions that can be asked are, does the process generate potential chemical or physical hazards? Are employees exposed? And is industrial ventilation through engineering control the solution? If the employees are exposed, then there are 4 pathways that hazards may enter the body: ingestion, inhalation, injection, and absorption. Reducing inhalation of hazardous vapors and ingestion of hazardous dust or aerosols is a focus of industrial ventilation. The impact on the employee resulting from harmful vapors or dust or mist will depend on the frequency of the exposure, the duration of the exposure, and also the magnitude of the exposure. The frequency, magnitude, and duration of the exposure will define its effect on the employee, being acute or chronic. An acute exposure will have an immediate or short-term effect on the employee. Onset in the near future, taking minutes, hours, days, perhaps weeks to develop. Hazards that may impact an acute effect are lead, carbon monoxide, and cyanide gas. Chronic exposure will have long-term or latent effects that take longer to develop, such weeks, months, or years. Compounds that may cause a chronic effect include asbestos or lead. And then depending on the concentration of the hazard, its exposure may be acute and chronic, such as exposure to lead. Based on the acute and chronic effect of the hazard, exposure guidelines have been established. OSHA limits are enforceable. Federal and state OSHA permissible exposure limits, PELs, are enforceable. The PELs have been promulgated from 1970 and later. Some occupational exposure limits are recommendations and not enforceable by OSHA. These are termed occupational exposure limits, OELs, and are standards that have been adopted by industry. Occupational exposure limits generally are not enforceable. These are recommended limits and are updated more frequently than PELs. There are several types of OELs. A few examples include the TLVs established by the American Conference of Governmental Industrial Hygienists, ACGIH. Threshold limit values are industry standards for acceptable concentrations of contaminants. There are two types of TLVs. First, there are the TWAs, which are a time-weighted concentration that are acceptable over an 8-hour period. While STELs, a short-term exposure limit, are concentrations that should not be exceeded more than 15 minutes during any 8-hour time period. Another example are the National Institute of Exposure Safety and Health, the NIOSH. These are recommended exposure levels. These exposure limits give directions on what compounds need to be controlled. Due to regulatory and recommended exposure limits, we now have an objective for exposure control. We want to control to less than acceptable concentrations. Acceptable concentrations are those as defined by OSHA or the company itself. If the company requires more stringent exposure control, consensus standards are those defined by the industry, such as the TLVs. The exposure control plan should be cost effective. Hierarchy of exposure control. Ideally, and at the very top of the pyramid, we'd like to be able to eliminate the occurrence or use of compounds and or processes that create the opportunity for employee exposure. Engineering control is next on the pyramid, and this requires a physical change to the workplace. And more than likely, this will include the addition of equipment to contain and treat the contaminant. Again, engineering control will require a change to the workplace. Administrative controls and PPE are closely aligned. For example, the employer would require that the employee wear personal protective equipment when cleaning up a spill. Another example of administrative control is limiting the time a worker is exposed to an airborne hazard. Engineering controls are features incorporated into the work process in such a way that the hazardous materials are contained within the process equipment or captured and eliminated from the work environment prior to personnel exposure. One example would be a local exhaust ventilation installed to capture welding fumes in production welding operations. And now, in order to implement engineering controls, we first have to have an understanding of some airflow principles. Understanding airflow is key to reducing employee exposure to airborne hazards. The flow of air between 2 points is due to a pressure difference between the 2 points. There are 3 defined pressures for flow of air through a ventilation system. We have velocity pressure, VP, static pressure, SP, and total pressure, which TP, which is the sum of our velocity pressure and static pressure. And typically, these are measured in inches of a water column. Velocity pressure is defined as that pressure required to accelerate air from rest to some velocity. Velocity pressure acts in the direction of flow and is measured in the direction of flow. Velocity pressure represents kinetic energy within a system. And finally, velocity pressure is always positive. Static pressure is defined as the pressure in the duct that tends to burst or collapse the duct. Static pressure acts equally in all directions and is independent of air velocity. And static pressure can be negative or positive. Finally, total pressure is the sum of our velocity pressure and static pressure and can be negative or positive. Figure A is illustrating the pressure contained within a duct, the static pressure. Note the pressure tube does not extend into the duct. This pressure represents the pressure difference within the duct from atmospheric pressure. Figure A is static pressure. Figure B illustrates total pressure. Here, the pressure tube extends into the duct and the tube is oriented so air flows into the tube. And finally, figure C shows the manometer that is used to measure velocity pressure. Normally, we measure only static pressure and velocity pressure and not total pressure. Velocity pressure equals the total pressure minus the static pressure. A pitot tube is used to measure and is a tube inside of a tube. And the static pressure is measured in the annulus with the holes on the side of the tube perpendicular to the flow. We can see where the P sub S arrow is pointed downwards. The total pressure is sensed by including the air being blown into the inner tube. Velocity pressure, which is the total pressure minus the static pressure, is measured on the pressure gauge, which is the manometer. Velocity pressure is always positive, and velocity pressure will increase as the velocity of air in a duct increases. Pressure and flow in the duct. Now let's use velocity pressure and static pressure to further define the flow of air in a duct. Our first important equation is the velocity pressure. Velocity pressure is Vp, and then we also have our density factor, Gf. V equals the velocity, which is always feet per minute. If we know the velocity pressure, the velocity of air flowing in the duct can be determined. This is the first equation allowing us to determine the air flow based on velocity pressure. To have a correct correlation between velocity and velocity pressure, a density factor is used to correct for temperature and elevation other than standard. The standard for air at 70 degrees and sea level is 0.05 pounds per feet cubed. Actual temperature is typically measured in degrees Fahrenheit or degrees Celsius, and in order to determine the density factor, the absolute pressure must be utilized. And degrees Fahrenheit would be converted to degrees Rankine, and degrees Celsius would be converted to degrees Kelvin. There are equations that provide this correction, as well as tables for both the elevation and temperature density factors. Once we have measured the velocity pressure, we can rearrange our equation and determine the velocity that causes the velocity pressure. There is this is because there is a direct relationship between the velocity pressure and the velocity within a duct. For a quick approximation regarding actual conditions, one can assume that the actual density and the standard density are the same. And if we make this assumption, then the density factor, the dF, becomes 1. However, if we have temperatures that are above standard, say 150 degrees Fahrenheit or greater, or elevations above 2,000 feet, it would be worthwhile to calculate the actual air density. The actual air density is a product of the density factor for temperature and the density factor for elevation. In the example above, we see that although each density factor itself, the one for temperature and the one for elevation, is not that significant, being 0.8 or greater, when we multiply them together, the overall density factor is 0.7, and that is significant in regards to being able to determine the actual flow. So if we do deviate from ambient conditions, it would pay to consider the density factor. The second important equation is Q equals VA, where Q is the volumetric flow rate in feet cubed per minute. V is our velocity, and A is the cross-sectional area of the duct. Cross-sectional area is the diameter of the duct where the velocity pressure is measured. Flow rate should always be stated in actual cubic feet per minute or standard cubic feet per minute to allow correct interpretation of the flow rate. Determining flow rate from measuring the velocity pressure and knowing the duct cross-sectional area is a great troubleshooting tool to determine if the flow rate of an existing system is what was originally designed and expected. Flow rate and its effect on other ventilation components must be considered. I consider hoods to be the first line of defense against exposure. Hoods located at the source of the airborne hazard represent the ventilation system and operator interface. Hoods are used to contain and control process emissions. A well-designed hood will reduce, if not eliminate, employee exposure at the hazardous contaminant source. And hoods are the single most important factor in establishing a ventilation system's volume and size and energy to reduce employee exposure.
Thank you, Vern. Those pictures were quite the difference between the before and after. Quite interesting to look at. So we have reached our second poll question. So remember again, you can answer the actual question in the next slide. So what does Q refer to in this formula? Q equals VA. So we have CFM, FPM, square feet, or temperature. And here's where you can answer your questions, and we'll give you all a couple seconds here. Giving you another 5 seconds or so, and we'll take a look and see. Okay, most people have it at 95% here, and I'm pretty sure that that was the right answer. Vern, CFM was the right answer?
That's the right answer, yeah.
All right, good. So most of you got that. Awesome. Clearly, I'm still working on my skills here. So good job, everyone. And we will continue with the rest of the presentation.
Okay, now we're going to talk about system effects, and they must be considered. A well-designed and placed hood will save money opposed to wasting energy and wasting money. When initiating an industrial ventilation design, the focus and challenge should be to remove the smallest amount of air with the greatest concentration of pollutants. If we are successful here, then we will have the smallest control system, and a smaller system is going to cost less to install, and we will invariably then have smaller fans and motors, and that system then would cost less to operate. And the hoods provide the first opportunity in the ventilation system to reduce airflow rates and meet objectives to reduce employee exposure. And we're going to talk about capture velocity. And hood capture velocity is key to controlling airborne hazards. Capture velocity is a minimum hood-induced velocity necessary to capture and convey the contaminant into the hood. Note, it is important to consider the distance that the hood is placed from the source, and here we're showing it as X. And depending on the source contaminant, there are various capture velocities that are required in order to assure that we're containing that and capturing that contaminant. There is a wide range of velocities we can see from 75 feet per minute to 2,000 feet per minute, depending on the source of the airborne hazard. Within each range, it is important to consider the toxicity of the source contaminant as well as the quantity of the contaminant. And also affecting the range within each source would be if we have any cross drafts due to traffic or makeup air. Depending on the service, hoods are configured to most economically reduce employee exposure. And we have some examples of hoods here. The first one is the canopy hood. And the canopy hood does rely on capture velocity. And these are good for more buoyant emissions where work does not take place above the hood. Next, we see a couple of examples of hoods, the slotted hood, and then a wider profile slotted hood. These hoods actually rely on control velocity, and we're not going to talk too much today about control velocity. We are focusing more on capture velocity, but our slotted hoods are used frequently in metal plating industries. And then where we have a push system with the push-pull slotted hood is where we have a wider profile, and by using the push air system, we reduce the overall air requirement. Again, the canopy hood is an example of a hood that relies on the capture velocity. And this, we can see in this photo, there's a flanged hood, flex duct with just a flange on the end. And again, this represents a hood that functions based on capture velocity. And it's important, what we're noting here is just the distance that we have from the source and the hood. Just moving that 6 inches, from 6 inches to 12 inches, the airflow required actually increases by 3.5 times, from 440 ACFM to 1,560 ACFM. So when you have a hood relying on capture velocity where there is some distance between the source and the hood, the placement of that hood is quite important. And we can see it here with a canopy type hood. Again, we have the equation that can be utilized, and there are various equations for different types of hoods relying on capture velocity. And here we can see the equation is Q equals 1.4 times the perimeter of the hood times the velocity by the distance x. So if we just increase that distance x, double that distance x, you are going to double then the flow rate required. So very, very simple concept for these capture hoods that rely on capture velocity to have them close to the source. Along with the distance from the source, another factor that affects the flow requirement is the geometry. And we see this effect with the hood entry coefficient F sub H. The reduction in velocity pressure associated with the hood losses is calculated as the product of the hood entry loss coefficient times the velocity pressure. The hood entry loss factor varies depending on the geometry of the hood. F sub H accounts for the loss associated with transitioning from the hood area to the duct area. And generally, hoods with tapers and wider entry angles will be more efficient in that they will have less pressure drop at any given flow rate. A bell mouth inlet hood, that let's see, the second from the bottom there, that has a it is the most efficient hood, and it has a hood entry loss coefficient of 0.04. Slotted hoods are unique in that they have 2 points of entry loss. There is a slack coefficient F sub S based on the standard design slot velocity of 2,000 feet per minute. There is also the hood entry loss coefficient, the F sub H, that results from transitioning from that hood plenum to the duct. Knowing that a slotted hood has two loss points, it is possible to calculate the static pressure. Along with those hood losses, the slot loss and the transition loss, we have to incorporate the acceleration loss in order to have the overall static pressure required at that hood. And so we're going to add the hood entry losses. And for this slotted hood, there's the two components for the hood entry loss. And to that, we have to add our acceleration loss. And that acceleration loss sometimes is termed the Bernoulli coefficient. And that is the amount of energy required to get the mass of air at the velocity that we need. And this is just kind of, again, geometry plays a great factor in the loss coefficient. The geometry with wider tapers and wider entry angles will be more efficient. The plain duct end type hood has a loss coefficient there on the left of 0.93, and simply putting a flange at the end of the duct end reduces the loss coefficient to 0.56. So we have less loss simply by having that flange on the end. And I think it's just worth mentioning that once we are able to determine these loss coefficients, and then along with the acceleration loss, we can figure out the static pressure of the hood. And if we have, with those, there's also then the hood flow coefficient CE, and that then allows us to determine the overall flow rate at that hood. And at this point, I'm going to turn it over to Dale.
Hello. We almost always use round duct in industrial ventilation systems. The only time you ever go to rectangular typically is if you're passing a duct through a confined space where the size of your round duct is not going to fit. So, plus round duct it has the same strength over that circumference, whereas rectangular duct, you're going to have, if it's wider than it is tall, you're going to have weaker spots, and calculating how thick it should be and what kind of stiffeners can become problematic for you. Velocity, like Vern was saying, velocity is very important. If you don't have the correct velocity, what you're going to end up with is what you see in this photograph, with the duct being half full of contaminant. That's problematic in that you've reduced your area, changing your velocity profile, which higher static, you're not going to get the overall or system volumetric flow rate that you need. And if it fills up too much with a material that's heavy, the duct could collapse and harm people in the plant and contaminate the plant if the material is bad stuff. Velocity rates that we use, if it's a vapor or a gas or smoke, we can go as low as 1,000 feet per minute. I actually did a project where we were conveying a powdered milk, and we had to go below that number, but typically for fumes and gas and vapor, we're in the 1,000, 2,000 range. For fumes that have metal smoke in them for welding, we go in the 2,000 to 2,000. For a very light dust, to be wood flour or cotton lint, you're in the 2,500 to 3,000 range. For dry dust and a powder, we're in the 3,500 range. For your average industrial dust, 35 to 4,000. We typically design it around 4,000 if it has what we consider a dust source. For a heavy dust, where you're going to get chunks of wood or particulate that's sand in nature, you want to go higher so you don't have dropout, because even though the system may convey heavier chunks of particulate, they tend to drop out and cause problems for you in the future in that ductwork. If it's a heavy or moist dust, like lead, cement, anything that has the ability to cling to the inside of the duct, you want to go up to 4,500. And we've even done on a rubber plant where the stuff stuck to the inside of the duct on a regular basis and posed a potential fire and explosion. We've gone as high as 5,000. Is conveying velocity critical to system design?
So we have a couple options here, fairly simple ones actually. So yes, no, and what is conveying velocity? So again, you can answer in the next slide, and then we'll go back to Dale here. He's going to show us some more here, but so this one, hopefully you guys understand the question. Give you a couple seconds here, and then I'm going to pass it on to Dale to go over the results. Okay, So
Very
we have
good.
a majority, 98% at yes.
And for those of you that didn't understand that the 1.3, not a problem, but the conveying velocity is how fast the airstream is moving. And in all industrial ventilation systems, the material is riding in the air. So we are only considering the air. The air is what's important, and you adjust the velocity dependent upon the heaviness of the particulate you're conveying. Flex hose, as you see in this photograph, again, flex hose is necessary in many systems, but you want to keep the length of that to an absolute minimum. What you see here in this photo, this thing has actually formed a P-trap in the duct. There's the equivalent of 4 90-degree elbows, plus flex hose, the inexpensive kind, is rippled on the inside wall, so the loss factor for the friction is much higher, like 3 times higher than it is for typical round duct. So again, you want to keep that to a minimum amount. The reason hoods sometimes move, but again, you could have had that duct higher so that when the hood did move, the flex hose would stay in more of a straight configuration. Elbow design. The one on the left, obviously you don't want to do that. That's a 2-piece elbow. You're going to get a lot of, if it's handling an abrasive duct, it's going to blow a hole through the end of that duct, through that elbow in a short matter of time. You want to go with that recommended elbow that has a centerline radius of 2 times the duct diameter or higher. The longer the sweep on that elbow, the greater the radius, the less friction loss or the less loss you're going to have in that elbow. Branch entries. Whenever you have a system, you're going to have, most of the time, multiple lines coming in. The top left is preferred. That's what we term as a T-on taper fitting, where the 2 smaller diameters equal the larger diameter going out. That blends the air in the most effective manner and lessens the chance of material falling out. Top center is not recommended that we go that route, because in that taper section, the air is actually slowing down. You want to avoid that straight 90-degree tap in, because again, if it's an abrasive material, over time it's going to blow a hole in the top of that taper section. When you bring 2 branches in to your trunk line in the same vicinity, you want to stagger those to get proper blending of the airstream, like you see in the left and center. The right, you want to avoid that, because even though if the areas of those 3 ducts are equivalent to the larger diameter, it's going to set up more turbulence, and you're going to get some really strange wear effects in the duct just beyond that fitting. So you want to make that nice preferred 30 degree or 45, whatever, but not 90. Flanges. We use flanges in industrial systems almost always. The only time we ever do without flanges if it's a material that could possibly leak where they want it welded, but flanges are needed. They help. It helps you join the systems or the sections of duct together in lieu of using a slip fit, big and small in connection like you would have in HVAC, or you would have a continuously welded joint that I mentioned. The problem with continuously welded joints is a lot of times this ductwork is 20 feet in the air. You don't want a guy in a basket lift up there trying to weld the complete circumference that far off the ground. And flanges are important for use as a stiffener when you're designing a system per SMACNA standards to prevent the ductwork collapse. SMACNA Sheet Metal and Air Conditioning Contractors Association they publish a book for round and rectangular duct, and you can go to the chart. It's based upon the diameter of the duct and the static pressure in the duct, as well as what class is the dust, with class 1 being a light gauge material or light dust material versus class 4, which could be very abrasive and higher concentrations. And an example would be if you have a SMACNA manual, you open it up to, let's say, 6 inches of negative pressure, you pick a 30-inch diameter duct for class 2, and if you went with the 12, it'll give you different options. You can go with a 12 gauge and not need any stiffeners, or you can go with a 14 gauge and have stiffeners every 20 feet. And again, it's designed so that it doesn't collapse because of the pressure, or the particulate that could build up in it. They've actually calculated those numbers based on as much as 50% buildup of material for a safety factor for you. This is a 12-foot diameter duct, and since those are 5-foot wide sheets of metal, those stiffeners are on 5-foot centers, and it's important that the duct doesn't collapse, especially if you have a 12-foot diameter duct. You don't want a failure in that duct when it's hanging, 20 feet in the air. That could be catastrophic. So flanges can be used as stiffeners. The losses that you have in all of your ductwork components are expressed in an F, or a loss coefficient, and they're always multiplied by velocity pressure to get the loss in inches of static pressure. We call them loss. It's actually the energy that you need in the system to convey material properly. For a hood, the loss is what it takes to accelerate the air from 0 outside of the hood up to conveying velocity 0.2. And hoods are also dependent upon the shape. Vern had that slide showing the different shapes of the hood. This is a bell mouth. It's the lowest loss hood you can have. For straight duct, the loss is caused by the friction factor on the internal wall of the duct. So the larger the diameter of the duct, the lower the loss you're going to encounter for that duct. But it's also dependent on velocity and system volume. For an elbow, we showed you an elbow with a 2D centerline radius. That loss is the result of turning the airstream within the duct, and the greater that R that you have, the less loss you're going to have. For a branch entry into the main, that loss is the energy required to blend the airstream from A and B where they join at C. And having that, it's also dependent on the angle. A contraction or reducer is, because Q is going to be the same, the area of the duct shrinks, so velocity has to increase. So by increasing the velocity, we're going to encounter a loss there, which is dependent upon the velocity delta between 0.1 and 2. An expansion, you see on the far right, you actually have a regain because the airstream is slowing down. However, that regain is not usually as high as what it is for a contraction. Duct systems, they can be designed well and efficient. What you see here in this photograph, the trunk line is tapering, meaning it's getting bigger as additional lines are entering, so that's good. The elbows you can see are long radius, that's a good design. The T's are entering in at 45 degree, which is a good thing. The flexos you see below, that's questionable, but this is a woodworking system where the hood is mounted on a track, an automated track where they're machining across a wide plane, so that's needed in this case. Control device. There's many types of control devices, not just dust collectors, meaning filter media inside of a box. You can also have a scrubber. You can have a cyclone or centrifugal collector, and you can have after filters, which may be needed after your initial control device. And then there are thermal oxidizers that destroy VOCs. And the idea of that control device is to treat the contaminated air after it's collected, and then you can discharge it to atmosphere or potentially send it back into the plant. And the control device can be used for all types of potential emissions. This photograph is at Charlotte Pipe and Foundry, where these two, I'll call them dry scrubbers. We're collecting an asphalt aerosol at a dip tank, and even though it's in the aerosol state, by the time it gets that collector and cools down, it's going to condense out into a liquid vapor that builds up on the inside wall of, in this case, they look like a bag filter, but they're much thicker. We call them candles. Whereas where this particulate sticks to the inside wall of the filter, and as additional droplets join, they become heavy, at which point they wick and drain out into the box. These filters were placed in 1970s style electrostatic precipitator scrubber. That was a maintenance nightmare. People had to replace parts and pieces on a weekly basis, which required a lot of shutdown, which shut the lines down. And by putting these in, we've saved them a lot of energy costs as well as maintenance costs. And as this is roughly a mile from where the Carolina Panthers play football, they used to have to shut the line down on Sundays because they didn't want any bad press. Determining loss, you want to usually start from your furthest point. You're hoping that's your governing leg. I like to check all of them near the end of the line. In this case, we're going from point 1 at the hood up to point A. We get a static pressure. Then we calculate the loss from point 2 to A, and you pick whichever is higher. That's your governing static pressure. Then you add from point A to B. You add for the dust collector, which in this case is a cartridge style filter, and typically that's in the 5-inch range. It goes out of the clean air plenum of the dust collector into your fan, from your fan to your discharge stack, which in this case is a no-loss stack head. At that point, you have the total, your static pressure for your system. You know what Q is, your volume. You can contact your fan guy, give him those 2 numbers, tell him what accessories you want for that fan, and he can, within minutes, because it's all computerized, he can give you the price for the fan you need for your system. Balancing. Whenever you do a system, you have to balance it. If you don't balance it, the fan will balance it for you, and the effects are not going to always be good. You can balance by design. This note says before 85 is the only accepted method that was taught. Balance by design is problematic. It's problematic in that you have to manipulate duct diameters and elbow configurations to try and match static pressure. When you do that, you can create high pressure, high velocities in the duct, and it'll wear out sooner. So your choice, and when you do a design balance by design, what gets installed is not always exactly what you have on paper, so it's not going to balance it for you. It'll steal air from the leg that has the higher static pressure and overload a line that has a lower static pressure. That's your junction point. So the alternative is a blast gate. With a blast gate, you can change the setting on the blade as to how far it extends into the duct. You can induce the static pressure you need to get only the volume that you need. And because blades can wear out, when you balance that system, you want to mark that blade, take a measurement, and record that so that when it's replaced, you know exactly where to set it when you go back. The fan. There are 2 types of fans, axial on the right and centrifugal on the left. In most industrial ventilation systems, we're going to be using that centrifugal fan. Axial fans are used, you can use those in possibly the return air line if it's a long run, if you're sending the air back into the plant or to another location. That diagram you see in the bottom left, there's an inlet box that's shown. Those are good accessories to purchase with your fan because they replace the 90-degree elbow. In most cases, the fan is on the ground. The duct from the collector or collection device is coming down. When you have just an elbow with not the proper amount of straight, you can overload the fan wheel, which can cause fan damage. You can also have an inlet damper on the fan or an outlet damper. And the unitary base, that's a nice solid base where you can plant the fan housing, the pedestal, and the drive. And there are other fans out there that are generally hybrids of an axial or centrifugal design. Fan wheels, if it's on the clean side of the dust collector, backward inclined is the way to go. The only time you can't do that is if the static pressure is high enough. You'll have a radial blade wheel, paddle blade wheel. And if the fan is on the dirty side of the system or the collector, you almost always go with a radial wheel blade. Fan curves, and at the fan manufacturers, they have a lab or a setup area where they mount a fan to a pedestal, hook it up to the drive, and they will record. They'll set a speed, and they'll induce static pressure and get the correlating system volume at those points and plot them as dots and connect the dot. and then it'll do it for multiple speeds so that when you see a fan multi-rating table, it will be a collection of those static pressure points, static pressure and volumetric points for multiple selections. This photograph is the early 20th century, a Kirkham Bloom installation at a woodworking plant. Back then, when you said dust collector, it was almost always a cyclone or centrifugal. It's coming up through the plant roof into the cyclone. In this case, we actually have, I think, what they referred to in those days as a doghouse, where any of the particulate that could bypass the collector, not spin out and drop out, is being blown into this huge box that has louvered sections so that the air coming out at a lower velocity. So hopefully any carryover material falls out within that box and not to the atmosphere. But again, the system, industrial ventilation system is, and especially woodworking, make sure you keep the plant clean. You know, those guys will be knee deep in dust if you don't have a collection system to protect the workers from breathing the dust, and also to protect the environment and the neighborhood from any dust that could pass through the collection device. Today, you can get your collector, if we're talking just collectors here, you can get it in cartridge, bag, you can get them wide, you can get them tall, usually dependent upon the real estate available for you to put that collection device. But today, with all the technology, you can get them with explosion venting, you can choose rotary airlocks, screw conveyors, you can choose your collector depending upon how you need to get rid of the material that you're collecting. And energy savings comes into play, of course. You can do it the wrong way. This is our first slide of shame here. I'm not sure exactly what's going on here, but it's not good. It's rectangular duct with round duct joined, and it's just bad. System layout impacts system performance and required energy. Really, yeah, in this case, somebody's removed the trunk line or capped it off, so obviously you're not going to be collecting anything here. Another slide of shame. Vern talked about hood. The hood is the most important part of the system, because if you can have the best system, the best collector, the best ductwork, if the hood is not in the right location or used in the right location, this is what you get. You know, this paint booth is the hood. It's meant to have the paint sprayed either inside it or very close to the opening. So it's not, you're not going to collect the dust unless you have that hood in the right location or have the operator use it in the right location. Too hot in here? Let's break out the fans. Man cooling fans are the enemy of a dust collection system in most cases. If it's too close to the hood, it will blow the dust away from the face of the hood, and what you get is a mess going everywhere except for where it was intended to go in that hood. Attack of the killer duct octopus. You know, this is the result of somebody not going to the professionals to design their system. They probably called the local HVAC guy and said, hey, I need to connect points A, B, C, and D and get them into this rectangular duct going right into the fan. Not good. System effects, another slide of shame. Anything that you do at the fan inlet or outlet that's not per how you should do it, you're going to have effects. In this case, they're breaking the airflow. It's spinning. It's turning it 90 degrees from the way it should have spun, and then they decided to add this 180-degree elbow, blowing it back the other direction. This is another system effect, having an elbow too close to the fan outlet. In this case, it's a two-piece elbow, so you have loss from the elbow being too close and not having a proper elbow. Questions?
Thank you, Dale, and thank you, Vern, both for great presentation. A lot of information here, so we're really running up on the end of the time here. So let's try and do 2 quick questions, but before we get to that, just one more time, just to remember that you do need to be present for at least 50 minutes and also need to pass the test here, 8 out of 10 questions before that tracker widget will show you the print screen. So make sure that you have completed both, otherwise you will not be able to get that PDH certificate. Once you get to that point, again, just go to that tracker widget, and if you see there the little orange arrow for print here, that'll pop up and you'll be able to do that. And you can come back at any time after the event for the on-demand version, and you can print that out if need to, as well as all of the resources that are on the side. So real quickly, let me grab a question here. So should your fan be before or after your control device? Dale and Vern, just make sure you're not on mute.
Oh, I'm sorry.
I don't know if you want to go ahead, Dale.
I'm sorry, I was still muted. Yeah, at paper plants where you have multiple lines feeding a large collector and those lines are not all needed at the same time, they typically have individual blowers feeding that cyclone. So in that case, yeah, it can be placed before. As long as you have the proper fan, you can always place the fan in front of the control device.
Okay, and one more question here since we are just about out of time. And again, don't worry if we did not get to your question here live. We will reach back out to you after the event and answer your question. So what are the most common problems you see during a system assessment?
I do a lot of system assessments, and it can be as simple as the fan rotating the wrong way, or the bags not being properly installed, or the pulse mechanism on the collector not working properly, meaning it's not getting the compressed air it needs to properly clean the bags. And a lot of times it's the hood. Like the guy says, hey, I've got this system that cost me $500,000, I'm not getting the dust. Well, the operators have moved the hoods outside that collection range that Vern showed you. So a lot of times it's low-hanging fruit. Well, it is for us, but those are very common. The first things that I check on a system assessment are to make sure the fan's operating properly, make sure that it's got all the belts that it needs, that it's rotating the proper way, and that the collector has been maintained in a proper method.
Great. Thank you, Dale. Thank you, Vern, for the presentation here today. And thank you to everybody who attended, and I hope that you got some good information out of this. Don't forget, if you go to secocertified.com, we do have 5 events that are available on demand, all with the PE credit still available. And next month, we will have at least first quarter of next year schedule up, so you can register for those events in about a month. We plan on having 8 events next year, at least, possibly more. So check back often, and we hope to see you at a future event. I am going to go quiet here, but the actual platform itself is going to stay live for about another 30 minutes so that you guys can finish printing out materials, take the quiz, do whatever it is that you need to do. And again, don't worry if you asked a question and we did not answer it, we will definitely get back to you. So thank you again for attending. We hope you have a wonderful day. Take care.